in Chem 221, if you took it at Mount Hood, or if you didn't take Chem 221, no worried, we use this table right here for solubility. And if you haven't seen this before, if you haven't seen it for a while, in the upper left-hand side are a bunch of ions, which when they form with a compound, they are always water soluble. So example, you can see up there that everything basically was sodium, potassium, ammonium, as well as nitrate, chlorate, perchlorate, and acetate. All of those are soluble all the time. So you could make a brand new compound. It would be sodium blah, 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 and I don't know what blah, blah, blah is. I've never heard of it before. It doesn't matter. Because it's got a sodium, I would say it's water soluble. It could also be blah, 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 nitrate, and again, I have no idea what that first part was, but the nitrate tunes me in as a chemist to say, hey, I bet that's water soluble. Now, remember that most of the ions of chloride, bromide, and iodide are aqueous as well, but there are three important exceptions, and those are silver, mercury, and lead 2+. So, for example, in the video we just watched, that was PbI2 forming. Most of the time, iodide is soluble, all right, but when it's with lead or silver or that mercury ion, then you're going to have an insoluble compound form. In Chem 221, we also talked about like how barium sulfate was a fairly common exception to the sulfate rule. We also talked about how most of the negative ions down here, most of those are insoluble, which means they would form a solid right away unless they are with ammonium. The alkali metals, remember, are everything in group 1A, so that would be potassium, lithium, sodium, etc., etc. So just to make sure we're all on the same page, I have here three examples on the right, and you can tell which is soluble and insoluble from where they are on the chart. So barium nitrate. Okay, nitrate is one of the ones that's always aqueous, so barium nitrate absolutely would be soluble. No exceptions to the nitrate, notice that too. Now, barium chloride, all right? Chloride is right there. Chloride is usually aqueous unless it's with silver, mercury, or lead. Barium is certainly not silver, mercury, or lead, so we would say that BaCl2 in water is soluble. It's aqueous, it dissolves. Finally, though, barium sulfate. Now, most sulfates are aqueous, soluble, all right? Barium is one of the exceptions. So barium with sulfate, we would say it makes an insoluble compound. And really, we should write this then as BaSO4 solid. If something is insoluble, that means you'll put a little S next to it. It's insoluble, all right? And if something is soluble, then you'd put an AQ next to it. So the first two were absolutely correct. Those were soluble, and you should write AQ. But this last one, it should be BaSO4 solid. Sorry, my S's are pretty bad here as I write on this. Barium sulfate is insoluble. It does not dissolve well in water. This is a quick overview of the rules we looked at from Chem 221. And this list does have utility even now. There will still be uses for it. But now what we're going to do is look a little bit closer as to why some of these, like barium sulfate, are insoluble, and also why some of them, like barium chloride and barium nitrate, are soluble. Like what's making it, and can we predict when it's going to precipitate, etc., etc. So let's consider taking sodium chloride and dissolving it in water. Now, table salt is what sodium chloride is, all right? And I used to, as a joke, put sodium chloride in my friends' like Diet Cokes, which was really dumb and immature, but, you know, it was, just a few years ago. No, seriously, it was a while ago. Anyway, it was kind of funny because when sodium chloride, it dissolves so well in water, or Diet Coke for that matter, that you can't see it, all right? Nothing happens. So sodium chloride, you can dissolve a lot of it in water. But the question is, can you dissolve all of it in water? If we're going to write an equilibrium, let's write it like this, where the precipitated version or the solid version is the reactant, and the ions that go into it are the products. So for sodium chloride, we would say NaCl solid on the reactant side, and then Na plus and Cl minus, the dissolved ions, aqueous, on the product side. And again, this is an equilibrium.
When a small amount of sodium chloride is added to 100 grams of water, it dissolves. If we add more and more salt, Eventually, no more can dissolve in this amount of water. The quantity of salt dissolved in this solution, about 35 grams at room temperature, is a measure of sodium chloride's solubility in water.
So in this example, it took a lot of table salt, sodium chloride, to not dissolve, all right? But that 35 gram number is important. That 35 grams represents, if you will, the capacity of that amount of water to dissolve sodium chloride, turn it into sodium ions and chloride ions. Once you get past 35 grams per 100 or so milliliters there, then the water no longer has the capacity to dissolve the sodium chloride. And that's when you begin to see the precipitate on the bottom right there. So we refer in science as the solubility as like literally a threshold, all right? It can be measured in grams or moles or whatever, but it represents the amount of a solute to dissolve in a given amount of solvent, all right? And when you get over the solubility, over that threshold, that's when solid begins to appear. But if you're under that threshold, and as long as you keep stirring things up, then the solid continues to dissolve. And all substances have this threshold, this solubility in water, and that's what we're going to talk about in this section. When we talk about solubility, it's very important to use the same form of solubility. So we'll always have the solid as the reactant and the ions that go into it as the products. Remember that as we go through this section. The silver, lead 2+, and mercury 2,2+ ions, those three ions together are called the silver group, and they have very similar reactivity. That's why they're called it. All three of those, if they react with chloride, bromide, or iodide, they do make insoluble compounds. So with chloride, you would make silver chloride, lead 2 chloride, and Hg2Cl2. The Hg2 2+ ion is a diatomic cation. It's two cations that are connected together with an overall +2 charge. It's a lot of interesting science behind the Hg2 ion. We're not going to talk too much about it here, but just realize it is one of the different things. Anyway, all of these ions, when added to a chloride source, they are said to be insoluble. They make solid precipitates relatively readily. They happen pretty fast. It doesn't take too much of any of these things to make the ions, and this can be useful if you want to separate the silver group from other ions.
When moderately concentrated solutions containing silver ions and chloride ions are mixed, the resulting solution is supersaturated with silver chloride. A precipitation reaction occurs until the system reaches equilibrium. In this model, the red and white molecules are water. Chloride and silver ions, gray and green respectively, are in solution. When they encounter each other, they bond and bind with other silver chloride molecules that have precipitated from solution to form the solid.
When you remember how many molecules are running around in any sample that we use, i.e. 10 to the 23rd water molecules or something like that, it's amazing that silver and chloride ions honestly can find each other, but they do, all right? There's like a natural inclination of them to actually want to bond together, which is pretty interesting. So when silver and chloride come together, like all ionic compounds, they make a three-dimensional lattice network. We talked about these a little bit in Chem 222, where you have alternating silver chloride, silver chloride, silver chlorides. Very, very strong. The ionic bonds between them, pretty tough to break. All of the salts, all of the ionic compounds that form in this experiment are said to be insoluble, all right, which means they make solids. But because there are 10 to the 23rd or so at one time, honestly, not all of them are forming solids. Some of them are staying as ions. And this brings up the idea of, again, of equilibrium. In reality, all right, we don't have all of the silver and chloride ions making insoluble silver chloride solid, all right? Some of them remain as little tiny individual ions. And this is the joy, if you will, of equilibrium. We can use equilibrium to describe how little or lot of of the ions you need. And you can also think about it then as how much you need to make the precipitation occur, i.e. what is the solubility of silver chloride? How much of it does dissolve per liter of solution, or how many grams can you get to dissolve, etc., etc. If the equilibrium has been established, then no more silver chloride can be able to dissolve, and you'll just start making more and more solid. And at this point, another term that's used sometimes is that the silver chloride solution has become saturated. And saturated just means that you are making solid, and it's going to be very difficult to go back unless you start doing other things. Saturation just means that the liquid literally has no more capacity to dissolve the ions. They start finding each other. All right. And when that happens, you see precipitates and stuff. In the video we showed earlier with silver chloride, it said that the silver chloride was supersaturated. That means that you have solid forming, but maybe if you'd stir it up a little bit, it would go away. Supersaturation is like a quick knee-jerk reaction, I guess, to when ions come together. In reality and stuff, they take a little bit longer. You have to let them stir and wait and stuff like that to see. Don't be too worried about that. Saturated just is another term for having a solid form. Unsaturated means that you are below that threshold, and really then you won't have any precipitate form. People have studied the silver chloride reaction in a lot of detail, and they find that the solution is saturated, i.e. silver chloride solid begins to form when the silver ion concentration is 1.67 times 10 to the minus 5 moles per liter. That's a pretty small concentration. It doesn't take a lot of silver ion to make this happen. The solubility of silver chloride then is also equal to this number, because if you go to 1.68 times 10 to the minus 5th, just a little bit more, that's when you're going to start making a solid. If you're at 1.66 times 10 to the minus 5, just a little bit under, you won't see a solid. So the solubility, again, is literally a threshold as to when you see solid and when you don't. So if you have a silver ion concentration that's just a little bit less than 1.67 times 10 to the minus 5 moles per liter, no solid. But if you get just a tiny bit more than that number, that's when you will see a solid. Chloride should be the same as the silver ion. When they measured the silver ion above, it was in a silver chloride solution, and silver chloride breaks down evenly to silver and chloride. The stoichiometry of silver ions to chloride ions is 1:1. One silver ion for every one chloride. So that means chloride and silver ions both are at 1.67 times 10 to the minus 5 moles per liter in this example. We'll talk about when those numbers maybe aren't equal in a later section. This is an equilibrium. Silver chloride is a solid, make silver ions and chloride ions as products. And remember, in this chapter, you always want to do that. Solids on the left, ions on the right. The solution concentrations of both silver and chloride ions, 1.67 times 10 to the minus 5. Well, we can define the equilibrium constant value using these numbers, because like all K's, products over reactants don't include solids and liquids, so no silver chloride solid. Silver ions and chloride ions count. They're both 1.67 times 10 to the minus 5, so you take that number and square it or multiply it by itself. 2.79 times 10 to the minus 10th. And if you think about this equilibrium constant, it's a number much less than 1. That means very reactant favored. That tells us as scientists, silver chloride as a solid wants to form. All right, it's going to be easy to form easy because that K is so small. The silver chloride really, really wants to form. And I would argue that PbCl2 and Hg2Cl2 both have really small Kcs as well. The numbers will be small because the solids form so easily. So notice here that the solubility is this number, 1.67 times 10 to the minus 5. The K value, the equilibrium constant, 2.79 times 10 to the minus 10th. Solubility is different than an equilibrium constant, and we'll come back to that in a little bit. This Kc that we calculated, 2.79 times 10 to the minus 10th, it actually has a special name. It's called a KSP, a solubility product constant. It's the product of solubilities. I guess that's where it comes from. Anyway, I don't know. But anyway, KSP is another kind of equilibrium constant. And KSP is used for figuring out when solids form and when solids don't form. KSPs are just as handy, arguably, as KAs, KBs, and all these other kinds of things we've seen so far. In this particular section, there is a handout I'd like you to look at if you get a chance. It's called the Solubility Guide. It's in the companion and it's on the website, but it talks more about solubilities and how you can convert a solubility to a KSP and KSP to solubility. Lots of cool kind of things in that handout, so I do recommend you check it out. Here are some representative KSPs that I just happened to find, and look at all of those KSP values. So first of all, it says 25 degrees. They are temperature dependent, and we'll talk about that later. But anyway, all of those KSPs are numbers less than 1. So what that tells you right away is all of these compounds, they will form a solid very readily. All right, there's barium sulfate. That was one of the ones in Chem 221 I wanted you to know. It almost always forms a solid. Calcium hydroxide, that'll be the purpose. We'll look at that in a future lab coming up, but that's very insoluble. Calcium carbonate, there's the silver chloride, silver bromides, etc., etc. All of these KSPs are going to be less than 1. There's a lot of cool things you can do with KSP, and we'll talk about those as we go through this area. But for right now, just realize none of these KSPs are numbers you have to know, okay? They're numbers that you can look up, use the all-powerful Google, whatever you need to do, and figure out what they are.
When solid lead chloride is added to water, a small number of ions are released into solution. Those ions can reattach to the solid, while other ions can dissolve. A state of dynamic equilibrium is reached, in which the concentrations of ions are constant and can be described by an equilibrium constant expression.
The KSP for lead-2 chloride is 1.9 times 10 to the minus 5, and we can figure out what the solubility of lead-2 chloride is from the KSP. What we can tell from the KSP is that because K is less than 1, PbCl2 really wants to form, but it doesn't explicitly tell us this solubility, like how many moles of lead-2 chloride will dissolve per liter before we start making any solid appear. And we'll talk about again how to go from KSP to a solubility and back and forth. So here's a question you might see. Which of the following correctly displays the equation used to describe the KSP for barium fluoride dissolving in water? Okay, so this is the question where first thing you must know is what exactly barium fluoride is, and that's a great question. Well, barium is a group 2A alkaline earth metal, so it has a positive 2 charge. Fluoride is a group 7A nonmetal with a negative 1 charge. So when barium and fluoride come together, it's going to be BAF2, okay? BAF2 is the formula for barium fluoride. So right away, this cannot be answer D. That's the incorrect formula for barium fluoride. Now, when you're writing a KSP expression, you always have the solid on the reactant side, and the ions that go into it are the products, all right? So if you look at the first one there, A, barium fluoride is right, but it's not going to go barium fluoride solid to barium fluoride aqueous. That doesn't sound right. The second one, B, looks a little closer, and remembering that fluorine is one of the 7 diatomics. Have no fear of ice clear brew. F is the fear of that one. So it's tempting maybe to think about it as F2, 2 minus. But the F2 part, the diatomic, only applies if it's neutral fluorine. And this is not neutral fluorine. These are the ions of fluorine. So if you're going to write fluorine as an ion, or the fluoride part, you want to write that as F minus. And you have 2 of these F minuses with barium. So in these 5 possible answers, answer C is the one you want. It's got the solid on the reactant side. It has the ions that make it up on the product side. Fluoride is individual F minuses, so there's going to be 2 of them. You're good to go. Answer E is close, but reactants and products are reversed. That would be like 1 over KSP, which might be interesting. But for a true KSP expression, solid on the reactant side, ions that go into it on the product side.